Okay. So it is, I know Dr. Roesch has a lot to present. So it is my pleasure to introduce Dr. Scott Roesch. He's a professor in the Department of Psychology at SDSU, where he teaches graduate level advanced and multivariate statistics. Dr. Roche's research expertise is in multi-level modeling, latent variable methods, measurement and meta-analysis, and longitudinal approaches to data analysis. Dr. Rose has a very impressive track record of being involved in NIH and other funded studies, including leading or serving as a senior co-investigator on 25 grants. And then he's also the primary statistical consultant on additional 23 grants. So he's very busy. And also serves as a senior research methods and statistical expert on our InStep P50 Alacrity Center at the Morris Cancer Center here at UC San Diego, the Consortium for Collaborative Initiative on Fetal Alcohol Spectrum Disorders, and on the California Evidence-Based Clearinghouse for Child Welfare. So in all of his spare time, he's also published over 250 publications. He is the associate editor for implementation science and also served as an associate editor for health psychology. One of the things I really appreciate about Scott is he also is really a committed and dedicated mentor and has extensive mentoring experience and co-publishing with early career faculty and trainees. I'll say on a personal note that my work would not be possible over many, many, many years, would not be possible without the expertise, collaboration, and the pragmatic approach that Scott brings to our project. So we're so grateful for
Are
his.
are you really trying to make me cry before I have to talk?
Yes, yes,
Okay.
I am. So Scott's going to present. We'll leave some time for sort of questions, and then I think Dr. Anna Lau is on, and she and I will facilitate or co-facilitate discussion and questions. So Scott, I'll turn it over to you.
Thank you very much, Lauren. Oh, good. It's already flipped back to me. Let me see if I can get the present. Can you all see this yet or no?
Not yet.
Not yet. Okay, share. Okay, I feel like it's coming now.
It looks like it's
Thinking about it.
yes.
Okay,
And now it just needs to be in slideshow. There you go.
perfect. Thank you. Thank you, Lauren, and thank you all for coming on a Thursday at 2 o'clock. Who wants to hear about power analysis on a Thursday at 2 o'clock? Very few people, I'm sure. So let me tell you something. That all sounds great when Lauren describes me like that, and it just means I'm super old. But what struck me when I was asked to give this presentation was how much all these things I've done in statistics, all these different analyses I've done, 30 years, power is still the thing that there's no one right way to do it, right? This is not an ANOVA where you point and click, you write some code in R, you get a p-value, get an effect size, and you go on with your life. We have done, probably just with Lauren alone, run the gamut of things where we had no ideas about effect sizes, right? We weren't sure about sample size. So we sort of guessed, and a grant gets funded. And then we go to the opposite side of the spectrum where we've got all of this previous data that tells us here's what we think the effect size is, here's what the interclass correlation coefficient is, which I'll talk about today. You know, everything has a reference for it, and things don't get funded. So it's one of those really fussy areas within statistics where, again, there is no one way. And I am absolutely going to be pragmatic, but pragmatic also means there's going to be things that I will leave out that reviewers might want to see, right? The ultimate way to do these sort of power analyses, regardless of its implementation research or something else, is do some sort of simulation study on your own. Right? In a program like M+, there's a Monte Carlo procedure. R has power simulations you can do. That's not what we're going to be talking about here. Again, I really want to make this pragmatic, but pragmatic does come with a cost. So please keep that in mind as we walk through things. So here's sort of what I have for us today. I'm going to talk a little bit. You always have to cover the basics, but I don't want to waste a lot of our time here with basics. So, yes, we know sample size is going to be important. Hopefully, we all have a general sense of power, what power is. I'll touch on that a little bit. But then, really, I want to get into let's just do it. What's different about implementation research specifically? And part of the primary issue is going to be you've got these things called nested or clustered designs. So you're going to be dealing with these studies where you've got children nested within therapists, for example, therapists potentially nested within programs. So you can't treat these observation as independent. And so I'm going to introduce this little concept. It's going to have a formula, but just so I can make a conceptual point to get a better sense of, okay, what does this mean for my power life if I do have these things called nested or clustered designs? So hopefully you've heard of those terms before. We generally use multi-level modeling, mixed effects modeling, which is a synonym for the same thing, to analyze this sort of data. So that's really going to be the primary nuance today. And then I just want to play. So I've got this little bullet point here that says shiny apps. So what I've made my life's work is to try to make all things statistical, power analysis in this case, easier for folks to do. And so there's these neat little online calculators that are called shiny apps, generally developed in R, that people can use to do quick and dirty power analyses. And that doesn't make them wrong, but it makes them easy to use. And I'm not going to be able to go into a ton of detail about how to use these things, but I do want you to see them. And I do want to manipulate values that go into power analyses so you can see what happens, right? What's my power if I change my alpha level, for example, or I change the effect size? I think it's really important to let you all behind the curtain a little bit to see how I do things, right? On these sort of programs. This bullet point below Power Up R, which is the one I will primarily show you here, which is free, is this particular program called Power Analysis and Sample Size, PASS. And that's the one I generally use. It is not free. It is all encompassing. But honestly, the free program I'm going to show you, Power Up R, does just about everything that PASS will do. So again, I want to show you both, but I'm going to focus more on this Power Up R than the others. So that'll, that's about 25 slides of what I really want to show you. Down here, we've got some power analysis examples that I hope I can get to all of these for. And then I'm going to talk about these additional resources, which are other shiny apps or references that I have found extremely important in my life, right? So again, I'm going to show you sort of a basic 2-level and 3-level design and how to calculate power for that continuous outcome, right? Pretty basic sort of stuff. But we know the research world is super complicated. We can have outcomes that are categorical. Well, how does that impact power? Well, I won't go over that in great detail today. I'll have a reference and a shiny app for that. If you've heard of what's called ecological momentary assessment studies, also referred to as intensive longitudinal measurement designs, there are little power shiny apps for that as well. I see names on this call right now who love this stepped wedge design. There's a link that can run that easily as well. So again, I'm going to have to take some liberties in terms of keeping this fairly straightforward in terms of how to calculate power from these nested and cluster designs. But no, there's probably 8 to 10 slides at the end that we probably will not get to, that will have information that hopefully helps you if you want to get into this area a little bit more. All right, so here's the obvious as we go to slide 3 here. Right. So again, the whole goal of power is to try to find some effect size that is powered. And sort of the basic rule is the more people you have, the more power you have, which is absolutely true. But when you put yourself in the context of a grant world, that gets a little more complicated, right? You have to think of the cost of collecting more data, not only if you're paying participants, but on staff. So everything I think about starting off is not just more is better. I mean, that is true. But the reality is that never really happens here. So yes, we want large sample sizes, but there's always a but. We want larger sample sizes because that's going to allow us to reject the null, say there's a significant statistical effect, which is what we want and what its power is geared to, but probably with the lowest sample possible, if you will, trying to think about the costs here. So yes, increasing sample size is a good thing. We're hoping we can find some statistically significant effects, but it's That also comes with the cost here. So we'll talk more about that because this issue of sample size is not going to be as straightforward as one N, if you will, 100 people, because we are going to be dealing with these nested designs, or we've got children, for example. What's their sample size? Nested within therapist. What's their sample size? How many therapists do we have? And then potentially nested within programs. How many programs do we have? Right? That there's a sample size there as well. And notice I haven't even said anything about whether or not you've got longitudinal data of any form, number of observations per child. So again, it can get really complicated, but the general rule is the more people you have, the better off you are. All right. So again, I'm going to show you this particular program and spend a lot of time with this Shiny Power R app. But when you think about what should I be using, it really is dependent on what your research question is. So if you go from your aims to some statistical analysis, you will be able to find some sort of Shiny app or power program that will allow you to calculate power, right? So it's really important to understand statistics right off the bat because that's going to dictate what you should be using. So when you think about the type of analysis being conducted, well, if you have a continuous outcome and you primarily care about whether or not your intervention group differs from usual care or control, that sounds like a little t-test. If you've got two or more groups or categories, well, that's some sort of ANOVA. That seems pretty basic. Again, it's going to be more complicated for us when we factor in a nested data structure, but that's going to tell you what you need to do initially. What is my research question? How is my outcome measured? And how is everything on the predictor side measured? The second thing you want to consider is the hypothesized effect size. And Lord knows how easy this is for us to do, right? There's lots of different ways to get at this, and none of them are perfect. So we're actually going to talk about this on a full slide. So not only what type of effect size you should use, and there are many, but what value or values should you be specifying, and how do we get those values, right? Effect size is massive. So not only is larger sample size important for power, but not surprisingly, larger effect sizes means you're more likely to reject a null, to say there are significant differences or associations. This third bullet point, which is another important one that I have here, because I think most people undervalue this. Most people who do power analysis do two-tailed tests, and they use an alpha value of 0.05. Right? So in the last 20 to 25 years, we've had this push to get away from alpha equals 0.05. So we don't necessarily have to use that. And my new crusade is, well, why are we talking about one-tailed test? I mean, what we're going to talk about in the slides to come, the examples I'm going to give you, are basically looking at whether or not some intervention group differs from some control group on some outcome that you care about. That feels like your hypothesis is going to be the intervention group is going to be better off than the control group. That sounds like a one-tailed test to me. A two-tailed test is a more conservative way to test something. And so in terms of power, that actually reduces your power. Right? So that's an understudied issue. I'm going to show you how that works in this Shiny app to actually help you, to give you more power if you're concerned about that. The fourth and final bullet point in terms of basics for me is, well, what power level do we want? And sort of the basic level that everybody uses is this power level of 80%. If I can be powered at 80%, life is pretty good. Does anybody know where 80% came from? What's so magical about that? I'm glad you don't. So this is from Jacob Cohen, who is the godfather of power analysis. He has a 1988 power analysis book, and that's just something that has stuck. Right, 80% seems to be the bare minimum. Right, and again, we're going to play around with this to show you. Well, what if we don't want to use 80%? Right, what if we don't know the effect size? Can we specify 80% and then estimate what effect size would be 80% powered? And the answer to all of this is yes. So this is these last two are the important ones to me because they're things that have been sort of set in stone in the power analysis world, using an alpha of 0.05 with two-tailed test to calculate power, and using 80% power as the benchmark to determine whether or not your effect size and ultimately the sample size you care about are reasonable. Right? So I'm going to get us to think outside the box, hopefully a little bit, on these last two issues. Again, we're going to be more complicated. In particular, we're going to focus on multi-level models because, again, when you think about implementation research, these are, by nature, nested data structures. Right? You've got kids or families nested within therapists, for example. Right? So again, the idea, we're going to talk about this thing called the interclass correlation coefficient, is that these observations, children or families, for example, are not independent units if they are nested within some higher level unit. So if we've got the same 4 families with the same therapist, they're probably more dependent than independent. And that's what these nested data structures allow for us to model. And we're going to use multi-level modeling to do that. So that's where the wrinkle comes in. That's where it gets a little more complex here. If that is not an issue for you, if you've got individual observations that are completely independent, then there are a myriad of things you can do to calculate power. G-power has been around forever, this last little bullet point at the bottom. Simple program to use, but it does not factor in nesting, right? So we need to understand what this nesting issue really is in the context of this. Effect sizes, right? I'm sure you all have heard of effect sizes. There are a number of these. And the one we're primarily going to focus on today is Cohen's d here at the very top, because again, what we primarily are going to emphasize in examples is whether or not an intervention group differs from a control or usual care group. 2 groups being compared. Cohen's d is perfect for that all the way through. But R is an effect size you obviously can evaluate. R squared and F squared come from Jacob Cohen as well. F squared is just a different version of R squared. Odds ratios, and there are many, many more that I won't bore you with. Now, what a lot of people don't know is, if I'm going to go to our first little website down here, is that these effect sizes are simply transformations of one another. So here's a little website that, I just clicked on for this link here. So here's a lot of different effect sizes we care about. Here's Cohen's d, here's Pearson's R, here's R squared. Not that I want to bore you with formula.
Scott, we can't see what shows up when you click.
Oh no, that's no good. Wait, let me see if I can. Sorry. Let me see if I can share to the website then, which I may not be able to. Just give me a moment here. Okay. I'm going to stop sharing for a moment just to see if I can then now share over to my website here. All right, this is definitely going to make life more exciting if I can't get this to come up here. All right, well, I don't want to waste time here. So you're just going to have to visualize this for me. Let me get back to this.
You might be able to share your whole screen and then it'll show what pops up for you.
Okay, let's do, okay, that should pop up the whole Zoom. So let me see if I can get back to this. Okay, y'all can see that. Now, hopefully if I click on that link, you'll be able to see that. Yay, okay, so here it is. Here's different effect sizes. Again, the main point of this was to show you, look, here's some formulas that represent how each of these effect sizes listed above and on that previous slide are just conversions of one another. So again, if we care about Cohen's d and we want to get a correlation coefficient, that's a simple little transformation here. So again, part of the pushback you get from some reviewers is, well, you're using the effect size R, you should be using D in this context. But the reality is, mathematically, all of these are related to one another. They're simple conversions. So this is a little website. If you ever wanted to know, transform your particular effect size into another version of effect size that you could use. Right? Now I just have to figure out how to get back to there. Okay, good. And this bottom one, I'm not going to click on. That's just another version of it if you care about that. The second thing to consider before we jump right into power, this is another, I think, underutilized power analysis index people can look at. The hardest thing when I talk to applied folks is we don't understand what Cohen's d means. So if a Cohen's d is 0.5, what is that telling me? So what people have tried to introduce into the literature are these things called common language effect size. I'm going to show you one right now, and this is specific to Cohen's d. So rather than trying to convince somebody a Cohen's d of 0.5 is a medium effect size, which tells us the mean for one particular group you care about, intervention, for example, is half a standard deviation greater than the mean from the distribution of a usual care control group. It tries to convert that to a percentage to give the applied or practical user some general sense of what the effect size means. All right, so let me take you to this. Hopefully this will have a seamless transition this time as I try to. Good, there it is. So this is a particular website that has lots of different statistical tests. As I scroll down, hopefully you can see them all. But let me just give you a sense of what this is doing. So again, we're going to keep it super basic before we start to get more complex here. So let's select the little t-test here. So if we have a Cohen's d value of 0.5, which is a medium effect size according to Cohen, this is what the CLES is going to tell us. That people in group A, which if that's our intervention group, are likely to have a higher value for the outcome you care about than a person in the intervention or control group. So it puts these differences between groups. It takes that Cohen's d and transforms it into a percentage at the individual participant level. Right? It's debatable whether this makes this more understandable for the users, but this is one thing you could actually use to convey information in percentage terms, which some folks like. So again, just another potential tool I thought I would show to you all. Okay. All right. Now, don't be totally flustered by the formula. I'm only showing you this formula to make a point here. This is getting us closer to how we want to think about things in terms of power in implementation science. When you have these nested or clustered data structures, you can't treat the observations, children, families, what have you, as independent. Right? So one of the things people do to determine whether or not you have independence or not is calculate this thing called a design effect, of which there are many. So the way I want you to think about this is we've got, let's just use a general term, clients at what's called level 1. That's our lowest level. That's where we have our outcome data. But each of these clients is nested within a given therapist, which we refer to as level 2. Again, the idea here is, when we're thinking about nested data structures, is that clients that belong to the same therapist are going to be more related. Right? They're not going to be independent units, and we need to account for that, not only in any statistical analysis, but specifically power analysis. And the primary indicator of that, from this little formula in the middle, I'm just going to focus on the ICC part, is this thing called the intercluster interclass correlation coefficient. It gives us a numerical index of how correlated observations are within a therapist, for example, in this particular case. Right? So if the ICC is 0, that means you have complete independence among your participants, which makes your life a heck of a lot easier in calculating power and doing statistical analyses here. Things get a little more complicated when the ICC is non-zero. All right, so in this little example at the bottom here, it's the same data structure. Now I'm going to talk about therapists, make it a little more specific. Therapists is our lowest level nested within clinics. So this little m equals 10 simply tells us that on average, we've got 10 therapists nested within each of these clinics. The ICC value we're going to play with is 0.10. Right? So these are values we're actually going to have to come up with when we get to the power analysis section to come shortly. I'm just pulling numbers out of a hat at this particular point. So when you enter those values into this little formula for the design effect, if that value comes back as 1, that means your observations are independent, right? So that means that therapists are not really nested within clinics in a meaningful way. They're independent units based on the data you've been looking at here. Well, in our little example, we've got this ICC, which sounds pretty small since the ICC ranges from 0 to 1. This value of 1.90 here basically tells us our sample size, or the number of therapists, would have to basically double in size to get at the same sort of statistical efficiency here, to have the same sort of statistical power. So the ICC really indicates whether or not our design needs to be more complex, which obviously impacts your power analysis. All right, so I'm going to ignore the next slide, which basically gives more details on that, because we already feel like we're running, I'm going too slowly here. So we're going to pick up the pace a little bit. So the question I primarily get when power analyses come into consideration is, what do I need? Where do I get my values? Right? And primarily people think about this only in terms of the effect size. Right? So there's lots of different places you can get this, and all have positives, all have negatives, right? A pilot study. Right? So you've got some, RO3 grant, small sample to get a general estimate of what your effect size might be in a smaller context of an implementation study that you care about. Well, the downside to that is what? You have a small sample size. So your effect size is probably going to be less stable. And so some reviewers could take you to the task for that. And they have, and a lot of the folks that I have worked with. So a better route, and what you're seeing more and more, is the second little bullet point is, right, there's something in the literature. A meta-analysis is a great option. Right? So we're going to talk about numbers we can grab from those studies. And then if you absolutely have no clue, you can use Cohen's cutoffs, primarily for Cohen's D, right? 0.2 is a small effect, 0.5 is a medium effect, 0.8 is a large effect. Now, obviously the downside there is it's guesswork. You're almost saying, hey, we're hoping for the best. Let's see what happens. And again, we've sold multiple different approaches here to multiple people here. In my world, what I have most confidence in is the second one, right? Like Lauren has a massive train of research now. So we generally have a pretty good sense of where the effect size should be. And as you see, as we move on here, we generally have a pretty good sense of what the ICCs, these interclass correlation coefficients, should or likely will be. So the more you know, the more you can defend it with a reference, the better off you're going to be always. All right, love this study. And I've actually seen in the last 2 weeks in the center grant renewal, seen Nate Williams' name thrown around and his approach thrown around. This is, to me, the ultimate here, right? This is a particular study that has documented the key design parameters for implementation strategy research that can be used in power analyses, right? So it's basically doing a meta-analysis to determine, okay, what can I use as my effect size? What are people finding in my area? What do I have for these ICCs? What are people finding in my area? And then there's this third and final one that is another one of these often looked elements here is, what's my R squared? Right? So beyond the predictor, even if we still care about, as Nate reviews in this paper, the difference between two groups, intervention versus control, just to keep it simple, on some outcome or outcomes of interest, you can incorporate covariates, other variables associated with your outcome, and that actually increases the power of your statistical test, and by implication, power analyses. So the classic way to do this is, if you have longitudinal data, it's using a baseline value or a pretest value as a covariate. Right? So the larger R squared, the more variance you're accounting for, it actually creates less error in your statistical analysis, so you need fewer folks. So again, there's going to be a little bit of an issue with that as I show you a table from Nate's paper. But again, that's an understudied one. Most people focus on how big is the effect and what's the ICC. So now what I'm going to do is show you a bunch of super cool screenshots that I love. I'm not going to go into a ton of specific detail about this particular paper. Please read it if you're interested with the reference up above. I show you the next 3 slides with these snapshots just to show the important pieces of information that some people are creating to help you determine or use values in power analysis. So let's put aside the fact what's standard versus standard enhanced. This is really a little graph that's showing us, okay, if we find all the studies that had these two conditions, what's the mean effect size here? Right, so that's, rolls really down here, sort of 0.40, which is sort of a medium effect size. So that might be an effect size you could use in your particular power analysis. When you're talking about comparative effectiveness, these are two different intervention studies, right? The effect size is a little bit lower, right? That's this vertical line down here, a little less than 0.25. So this is using existing data, which may make you feel uneasy because these effect sizes are relatively small. But again, they're aggregated across studies, and that's something you can use if you're not really sure what you should be specifying as your effect size. The next table I really love. I know this looks crazy busy, but this actually gives you the same information, but by type of outcome, type of implementation outcome, how it's been measured. And this is a very, I know it looks busy, but it's a super impressive table. So if I've got an outcome that's adoption, that's my implementation outcome, right? The mean effect size for that outcome in the studies that were reviewed in this paper is 0.44. That could be your value that you use as an estimated effect size here. All right, so that's what's kind of neat about these studies, and there's more and more of these being done over time, is right, you don't have to use Cohen's guesswork of 0.2, 0.5, 0.8 for Cohen's d. These are all Cohen's d values in table 2 you're seeing here. You can actually use something that's rooted in evidence. Right? And that's, again, the more you can defend the effect sizes you use in power analysis, the better off you're going to be. This is where it gets a little more difficult. Again, I don't want to make a huge deal about this, but this gets at this issue of nested or clustered data structures, ICCs. So Nate has here in figure 2 the ICC values. I'm going to focus on the middle one just as a, for example here, this is from a 2-level design. So for example, children nested within therapist. We have no idea what the ICC is. We could use this mean ICC value here, which is a shade over 0.1, which suggests there is some dependency in your data that needs to be accounted for in the power analysis. And here's a reference we can use to specify this. And I don't want people to totally freak out here. This is longitudinal data, repeated measures data. The ICC is much higher, as it always is. So this is one of the first places that I saw, at least, implementation science and beyond, that was providing researchers some roadmap for trying to determine values to use in implementation power analyses. So I love this paper. It's one of the best I've ever seen. Last little slide here. Again, I mentioned this idea of this understudied design parameter for power analysis is R squared for covariance. So again, these are variables beyond the two groups you would want to compare, for example. And he gives values based on the literature of what R squared has been found. So at level 1, right, small little R squared value, a larger value for R squared, and a relatively medium value for level 3. So again, these are the harder things to specify because covariance can be anything. And they can be very research dependent here. But this was the first paper I saw that actually said, hey, here's what we know. And again, this is the sort of thing people should think about more. Well, what if random assignment doesn't work? Well, then we probably should be including covariance. Covariance enhanced power that equalize groups you care about. And this was the first indication of, hey, here's something we can use. Here's values we can use to try to get at that. All right, so now what I want to talk about, really the fun part for me is getting to the nuts and bolts and showing you this sort of thing. So let me click on this little website that hopefully you will be able to see shortly. All right, so this is, I'm going to go straight to power because again, I think we're running tight on time. So I'm not going to talk about this thing called the effect size contextualizer. So this is a particular website on causal evaluation, right? If you care about
we're still not able to see the website.
Oh, darn it. Okay, sorry. Let me get back to the share here. Go back to my screen. Okay, tell me when you can see it. All right, good. I can see it on my phone. Perfect. All right, so this is the little website, and you all have the link now as well. So if I just scroll down here, right? So this is a wonderful free program. We're going to play around with it here momentarily. So it's called Power Up. Right, this is what we're going to play with primarily when we compare about main effects or differences between two groups in calculating power. There's also one available for moderator analysis. There's also one available for mediator analyses. So it's got sort of the 3 primary statistical models we care about. All 3 will account for clustering at 2 levels, at 3 levels, and never do this, even 4 levels. So again, it's got a 4-level option. It's completely free. I'm going to show you the online calculator. There's also Excel versions of these as well that are part of the slides later on in the story here. All right, so this is, again, I just love this program. It's got all these great references. These are unbelievably talented multi-level modelers here. All of these packages are developed in R, but you never have to use R. They're all Shiny apps, or they are developed in Excel here, right? There's tutorials. It's just a wonderful thing. All right, so now what I'm going to attempt to do is get back to our little share option. Go here, and I'm actually going to go to the Shiny App Online Calculator. So here it is. So again, when you're thinking pragmatic, this is pragmatic. We're going to specify a number of values on the right-hand side here, and we're just trying to figure out what our power value is going to be, right? So there's documentation for all of this. There's a huge manual that walks you through things. I'm just going to, again, try to be relatively quick so you can see the important things, elements here.
Can you reshare, Scott?
Oh my gosh, yes.
I'm putting the links, folks, in the chat so you can also have these links, save these links.
Yeah.
But it worked before with the last one. There you go.
Okay, there we go. Hopefully it stays on here. Okay, so what I'm going to focus on to the left-hand side here, right? This is where we specify our value. So if you care about differences between two groups, intervention versus control, that's what this program refers to as a main effect. Just to show you can also look at moderator analysis. Oh, and it just went out on me again. Oh no. Okay. All right, I might just have to jump out of here, Lauren. And we'll just do.
Well, folks have the links.
Okay.
I put the link in the chat so folks can play around with it.
All right, so just what I did to cover myself a little bit, let's go to the next slide. So at least hopefully you can see, or you have seen on the left-hand side, or where you're going to specify values for a power analysis, right? So up here in our little example, I was going to walk you through and change parameters. Our two-level data structure we're going to start with is clients nested within providers. So again, the idea is these clients, whether they're children or families or parents.
And can you go back to your slide, Scott?
Oh my gosh. It seemed like such a good idea when I did this. Good. Okay, sorry, there we are. So I have these all color-coded to give you a sense of what needs to be specified. And so pragmatic, now when we're talking about real-life nested data structures and implementing research, pragmatic is not as pragmatic as a little t-test. But this is as pragmatic as we can get it. So what I'm trying to show you here is on that website, you can actually specify these design parameters to calculate power for a two-level design such as this. So our level 1 is going to be clients. Our level 2 is going to be providers here. So there's a couple of things you can do. You can either estimate power, right? Not set it at 80%, the magic number, or you can try to estimate the effect size. So in this little example, we are specifying an effect size of 0.50 for Cohen's d. Right, so now you need to specify all of these other design parameters. Here's the type 1 error rate. Here's our alpha. We're going to use 0.05. Are we using a two-tailed or a one-tailed test? And I'm not expecting everybody to learn this little software right now. We're just going to keep it as a two-tailed test for now. You can identify any covariates you have at the provider level. And then you can specify your ICC, which again, this is a major element. So what's the ICC? How much dependency do you have in your data for the clients nested within particular providers? You specify that value. You can specify R-squared values for level 1. So you can have covariates at the client level or level 1, and at the provider level, level 2. This third from the bottom, average proportion of providers randomly assigned to treatment condition. This suggests we have equal numbers of intervention and usual care groups, right? It doesn't have to be. So that's what's kind of neat about this little program is if there is a split, a non-perfect split, or you expect you're going to be able to get more usual care than intervention, you can change that little ratio here. And then you can specify the number of clients per level 2 unit. So this is saying we've got 10 clients for each of these providers. And our initial guess is that we've got 30 providers here. So those are the initial parameters we play with. And what I was hoping we would be able to do is I would just show you what happens, what power is calculated, and then we start playing with things. This is how I literally do it. So this is my starting point. And if I run these specifications and power comes back as less than 0.80, we've got to change some things, right? So you've got to think about, what should I be changing here? Do I need a bigger effect size, which always helps? Do I need a lower ICC right here? That always helps improve power, right? So those are the games I play. It's just sort of manipulating some of these parameters to try to be able to send Lauren an email at some point saying, hey, here, we're powered at 80% with this effect size, with this ICC, with these R squareds for the covariates here, right? So that's the game I sort of play to try to get some numeric values that help folks. All right. So fortunately, this is a screenshot of what we found. All right. So here's all those values, and what this little R Shiny app reports back to you is a power value, right, for the specifications that we have here. So this suggests we're not at 80%. So we need to do something else. So again, now you get to decide, okay, what should I change over here? Again, you can make the ICC smaller, which makes those observations more independent. That helps you with power. If I were able to scroll up, you would see the effect size. We can make that a little bit larger. That helps you with power. All right, number of subjects at level 2, that helps you with power. That's the cluster level. So again, that's the game I play. When you're thinking pragmatically, a program like this will allow you to specify a starting point, and then you just sort of alter the various parameters here on your left so that you can achieve the power you want, but also achieve the effect size and the sample sizes, because they're going to be at multiple levels, that you're going to be able to defend to reviewers. And that's always the hardest part, is what I can tell the folks I work with all day long, here's what you need to get at least 80% power. It's another fight altogether to determine whether or not that's believable. But again, that's where you fall back on articles like this Nate Williams article. It says, hey, these effect sizes and ICCs are consistent with what we're finding in our broader literature or specific literature. That makes these things much more defendable, right? So hopefully that didn't seem so bad. This seems way easier than running some simulation study in M+ to generate power, right? I think I don't know, I love this one. It's super nifty. All right, now let's change it up a little bit here. So same sort of structure here. The only thing I've changed in this little example is I've specified 80% power. And what we're trying to find is, what's the effect size? Right, so we've changed up what's the unknown. Everything else is the same. We're still at two-tailed test, still alpha 0.05, still the same parameter values as previously. But this is the other tact you take. If you're not really sure what your effect size is, but you think most people they feel pretty good about 80% power, it's almost working backwards in a little bit. What effect size is going to be generated here? So if we ran that little Shiny app, here's the point estimate for that effect size, roughly medium. And it's a wide confidence interval here, which tells you, right, sample size is still a little bit low, but what do we report in grants? The point estimate. All right, so that's another way to play around with this, is if you don't know the effect size, but again, like an agreed upon value for power is 80%, right? Then estimate the effect size and see what you get. And same sort of thing here. If I felt like I needed an effect size to be lower, 0.4, right? I'm going to have to manipulate some things over here. Specify a lower interclass correlation coefficient, increase the number of level 2 units in this case, just so I can get the effect size that I want. But again, ultimately selling this to somebody is a different issue. All right, here we go. So now we're going to talk about a 3-level design. Y'all can still see that? Yes, we're still on slides. So this is getting us closer. When I think about the center renewal and the stuff I've done with Lauren and her group, right? 2-level is pie in the sky. That's not reality. 3-level nested data structures are more of the norm. So that's what this example is really trying to show you. And I have, for pragmatic reasons, hid what's going on at level 1 and level 2, which I just walked you through previously. When you're talking about adding a 3rd level to your nested data structure, site, program, clinic, whatever you want to call it, you have another set of parameters that you need at this level. So here's the number of level 3 site covariates. We're going to specify no in this case. You can specify the proportion of variance In the outcome, that's simply the ICC at level 3, which makes it more complicated because now you've got an ICC at level 2 you've got to specify, and an ICC at level 3 you have to specify. You can talk about the proportion of variance explained by any covariates you have at this third level, and then you've got to specify not only your number of sites, but the number of level 2 units, providers in this little example, nested within sites. So it gets super complex, but there's no real way to make this part of it easier. I mean, if you really think about it, if you take the R squared out of this for covariates, really what you need is effect size, power, number of people at all 3 levels, and the ICCs at level 2 and 3. I mean, that's really what you need, which is a lot, granted, but it's necessary given the complexity of these sort of nested designs. We run this analysis. Unfortunately, your power is less than 80%. So here's what's interesting, painful when you start dealing with designs that are above 2 levels is, if you go back to the previous slide, there's the number of sites we're dealing with. This is the sample size at the highest level. And if this is where your randomization is in a cluster randomized design, you're basically saying you've got 5 sites in each of these 2 groups, intervention versus control, which is super low, but that's the reality of this sort of data a lot of the times in implementation science, right? So you go back to this, well, how can I increase this darn power number, right? 0.571 is not going to get it done. The easiest way is to increase the number of sites, but that's also typically the most impractical way, right? You're not going to be able to just magically come up with multiple sites. That gets much more expensive. So you got to think about, what can I do to help power if I can increase that value from 10, right? So again, I typically always go back to, okay, we got to reduce these ICCs. The more you can make these particular levels independent, lower ICCs, the more power you get. The other way to increase power is don't do 2-tailed tests, do 1-tailed tests. Right? So this is the harder part, is trying to figure out, okay, what can I change if I am just stuck on a small number, which you traditionally are, at the highest level of this data structure. And there's no 2 ways around that. I mean, I think we were fortunate in this signature R1 where we had this ICC at this 3rd level, which basically is your sample size, that was ostensibly 0, right? That helps with power. So if you come back and your ICC at level 3 here, doesn't even have to be a massive number, 0.05, you're going to need more than 10 sites. You're probably going to need 18 to 20 sites to be powered to sell this to somebody. So that's always been the challenge on my end is, look, I know the practicalities of this implementation research. You generally have to use cluster randomization. It's just so difficult to randomize at the individual participant level, children, families, whatever it is. So power is always going to be challenging in that context. And not to make you feel even worse, but to make you feel worse, we're simply trying to find, in this little example, the difference between 2 groups, intervention and control, or usual care. When you start thinking about moderation and mediation, which are typically lower effect sizes, 3-level designs are really hard to power. Absolutely. It's just super complicated. Okay, sorry, I can't see. How am I doing on time?
We should probably wrap up in a few minutes to leave a couple of minutes for questions.
Yeah, for sure. So again, that Power Eye Shiny app is what I've been playing with. I wanted to show you, I'm not going to go to this, I'm not going to any more websites, but this is the program I generally use. This is called PASS, Power Analysis and Sample Size. There's a link if you want it. It's not cheap, but it literally has every single power analysis for every design on the face of the earth here. And so what I have highlighted here, these are cluster randomized designs, mixed models, 2-level versus 3 models. Fortunately, I took screenshots of these. It just makes everything much easier to run analyses for power here. And what it generates, I know this looks like a nightmare, is you can generate simulation studies automatically. Right? You're not writing code, right? You're simply clicking in values here. Right? So here's a bunch of values we've played with. This little column is different effect sizes that you can test simultaneously, different number of measurement occasions, 2 time points, 3 time points, if you've got longitudinal data. And then what I really love about this which you can't really see, but at the very bottom here, it generates an automatic write-up. I never use it, but it gives you a description of the power analyses you've just run in grant-like language. And that's how they know they can charge you a lot of money for this, is they're basically doing all the work for you, other than you've got to provide the values for the design parameters. So unlike the Power R app I just showed you, where you've got to run models individually multiple times, change the ICC, this allows you to do that in one fell swoop, right? I can use any effects. I can specify effect sizes, multiple values for that, and run things simultaneously to see if I'm powered here. So cool, but expensive. Okay, we're not gonna have time for it. Here's a little example of an interaction term, moderation. Just to show you the sad story when you're talking about nested data structures and power for moderation interactions. The take home from there is it's hard. Mediation, I don't have a ton of time for either. Again, so walk yourself through this. And if mediation, when you're talking about multi-level data structures, here's a representation of that. Nate Williams has another incredible paper on that. Here it is. It gives you a general sense whether or not you would be powered for mediation. The general conclusion from this article is, right, you need 40 clusters at the highest level to be powered for mediation. Now think about that. The example I just gave you all in that Shiny app, it had 10. Right? That's just to find a main effect difference between two groups. Mediation, you need many more clusters if you have randomization at, say, a level 3. And so that's sort of Nate's point here is he shows you, again, I don't worry about what the numbers represent. Here's the take home from this particular slide for mediation is all of these blank little cells here show you how hard it is to power mediation when you're talking about 3-level designs. Right? So in this table are only sample sizes and effect sizes for which you would be powered to find a mediated effect using a 3-level design. These blank spaces suggest if you've got smaller medium effects, life is going to be difficult, if not impossible, to sell to a reviewer. Right. So again, that's this great study by Nate. He does some incredible stuff. Okay, missing data, please read that. That's important to evaluate. We're talking about different programs, different Shiny apps. This is one that's specific to finding cross-level interactions. If you care about repeated measures nested within children, families, therapists, whatever, this is specific to cross-level interactions. Right, here's repeated cross-section analyses. There's a Shiny app for that. And just trying to show you as much stuff as possible. Again, if you've got repeated measures data, we've used this a lot in grants. It's a program called RMAS, which is, I think, underrated for sure. We'll skip, this is a sort of an intensive longitudinal measurement power analysis program. If you care about growth modeling, if you're familiar with that, there's a Power Shiny app for that as well, right here. And then the last slide basically shows you how to calculate power for pilot studies. It's got a special correction for that. And here's another resource if you're looking at intensive longitudinal design. So, I mean, for here, we're not talking about, baseline 6 months, 12 months, 18 months, for example. These are for more ecological momentary assessment studies where you've got daily assessments or multiple assessments per day. There's a power analytic approach using this little Shiny app for that as well. So again, there's lots of specialized ways to get at this power. None of them are perfect. They all have their warts. And the biggest wart of all is if you've got more than 2 levels, it's tough, right? There's no way to make that pragmatic other than to play around with some numbers. Effect sizes obviously are hugely important. And then interclass correlation coefficients, to me, are the second most important thing to get powered here. The more those values are smaller, and smaller reflects reality, the easier it is to show folks, hey, we're going to be powered to find differences between these two groups and hopefully down the road moderated effects. I can tell I talk way too much as I get older because I didn't get through half the things I wanted to get through.
It's just that you're so much wiser for all the things.
So
So,
I know we only have a couple of minutes, but let me just say before people potentially, if you have any questions that you can't get in, just shoot me an email. I'm happy to answer those for you. And I realize that was fast and wonky given my share screen issues.
well, Scott, I just want to thank you so much for kind of opening that black box of what's happening when we are, frantically trying to write up a plan and to power our studies appropriately. It really helps us understand what's going on, and the reality of the complicated context that we're working.
Yeah.
We will share the PowerPoint that will be available. The recording will be available for folks if they want to go through it. There's incredible resources in the slides that you put together, so I encourage folks to access those. So thank you again, Scott. This was wonderful, very helpful, and thank you all for being here. Take care.
Okay. Bye, everybody.